So, what we're going to talk about now, this is the second unit, and it's all about statistics and intention. And don't worry, this is not a course in mathematics, so we're not going to learn any new math for those people who are afraid of that possibility. So let's see where this leads us. Why statistics? Well, statistics are used, data analysis is used in really all forms of science. Anytime a researcher does any kind of testing, any kind of work, it creates data, and you need to analyze the data and figure out what information hides in that data. And one big difference between, I guess, what I would call the hard sciences and say something like paranormal science, which some people would call it not a science at all, some people would call it pseudoscience, sort of derisively, and other people might refer to it as a soft science. Same is true with philosophy and psychology and psychiatry, etc., etc. All sort of soft. And rather than get into the actual details of what makes one hard and one soft, I think it's sort of obvious that measuring the speed and the weight and the size of an object is a very definitive, measurable thing. And those are things that are involved in hard sciences. Measuring things that are not quite as definitive it's a little bit harder to do that, and the results are subject to a lot more interpretation. So if, for example, if you were to have a medium do a reading for someone and they were to identify 25 different facts that they were able to read in their reading. Maybe one of the facts is that the subject had a brother and a sister, and the brother was older and the sister was younger, and they were from the Midwest, and then they moved to the West Coast, and things like that. Well, each one of those is a particular fact, and you can go through, and researchers do this, where they go through those facts. They itemize them, they list them, and they determine which one of those are objectively true, which ones are objectively false, and which ones may be indeterminate. And then they come out with some statistics to describe how accurate the reading was. So that's a sort of a pretty typical scenario. And so really what we've got here is that in the case of paranormal activities, statistics are much, much more important, or are actually indispensable part of the process, whereas in maybe some of the hard sciences, statistics aren't always quite as necessary. So the other thing is the scientific method in general. The scientific method is all about coming up with an idea, maybe a theory, and designing a test to prove or disprove that theory. And let's say, for example, a physicist came up with a test to determine the weight of an object. And they would write a test procedure, they would run the test procedure, and they would decide whether they thought that was a valid test. If they did think it was a valid test, they would publish those results. Other scientists could take a look at that procedure. And one of the key aspects of the scientific method is that other scientists can take that same procedure, run the same test, and get the same results. That's really an important part of the scientific method. That's been used for hundreds of years, and it's worked. The problem with the paranormal research is a lot of these things that researchers are testing end up not being very repeatable. And that is a major issue for conventional scientists, because if it's not repeatable, that means it's not true, or that it's only sometimes true. And so that is really one of the big stumbling blocks, one of the big barriers that are keeping traditional scientists from buying into a lot of the sort of paranormal researchers' conclusions. And I guess what I wanted to say here is that if, for example, a medium were to identify correctly that a person had an older brother and an older sister, and the older brother's name was something that started with a J, and the older sister's name was something that started with a T, Sort of sounds like Teresa, and they lived in California, right by a mountain, and whatever, on and on and on. I could make up some sort of scenario. And then we were to create a list of facts, and we were to find out of the 100 facts that the medium correctly determined 90 out of those 100 facts. The question is, and so let's just say that happens. I think any of us would say, if you were able to identify 90 out of 100 facts correctly, there's probably something there to be interested in. The problem is, if that same medium did another reading a week later for a different person and was not as successful, does that cast doubt on the original reading? And so the scientific method requires that a test be repeatable consistently to be valid. And what I'm saying is, in paranormal research, that's never going to happen. And so if you are setting a standard that requires that sort of consistency, you are never going to be satisfied with the results you get from a paranormal researcher, which is unfortunate, because I think there's a lot that the paranormal researchers are uncovering that we need to pay attention to. So there's another way of looking at this that I wanted to throw out there, and it has to do with taking a look at each one of these tests or each one of these events and looking at it statistically and figuring out what are the chances that the results that were found could have been found, and treat each one of these as a separate activity and look at the statistical probability of each of this thing happening to decide whether or not it's something that's valid. So that gets back to statistics. The other thing I guess I want to just give you a couple of examples that really look at covert versus overt. And when I'm saying covert versus overt, I'm saying maybe the obvious versus the subtle, for example. A lot of the things in this world are subtle, but that doesn't mean they're not important, and it doesn't mean they're not true. If the only things we will believe, the only things that we find true, are the things that are obvious, we are going to miss a lot about our world. So, for example, starlight. So my question for you is, can anyone tell me, where are those stars during the day? When you look up at the sky, why don't you see those stars? Is it because the stars aren't there? Is it because something about the blue in the sky filters out the starlight? It blocks the starlight in some way? Well, it turns out that neither of those things are the case. The stars are, yes, still there. They didn't go away just because it's daytime, number one. And number two, the starlight is still there. Those stars are shining with the same intensity they always have. It's just that you can't see it. The question is, why? Well, the answer is actually pretty simple. Your eyes, during the day, have to adjust by adjusting the pupil sizes. They have to adjust to the bright light of day. And when you adjust down, as any photographer knows or cinematographer knows, if you adjust down the aperture of your eye, the pupil gets smaller and smaller. It lets in less and less light. You're not going to see dim light. You're only going to see bright light. So in fact, those stars that are completely invisible to you during the day are still there, are still shining. And not only that, but the light from those stars is still going into your eye, still hitting your retina, and theoretically can still be seen by you. Unfortunately, your visual senses are being overwhelmed by the bright objects in the scene, by the sun, by the clouds, by all the objects around that are reflecting that sunlight. So I guess I just wanted to use this as an example or an illustration of the fact that starlight is a subtle thing in the day. At night it's not so subtle, it's very bright. But in the day it's very subtle, and so subtle that you can't even detect it. But it doesn't mean that it's not there. It doesn't mean that starlight is somehow not true. All right? Another example I'd give you is this. How many people here have seen a satellite before? And I don't mean up close and personal. I mean at night, looking in the sky, how many people have seen a satellite? For those people who haven't, it's pretty simple. All you need to do is sit down or lie down and look up at the sky and sort of stare at one particular spot in the sky. You can either just gaze or you can actually focus on a particular star in the sky. And if you wait and just are patient, you will see a motion out of the corner of your eye. You may be looking here and you all of a sudden maybe see a motion over here. Change your gaze and move towards that moving object, and if you don't see it, again, stare at that new spot in the sky. And if you do this a few times, you will eventually find that object that's moving. And assuming it's not a plane, and planes are pretty recognizable, and so if it's a plane, start over again. But it'll look exactly like a star, and it'll be moving at a very, very constant speed in a straight line from horizon to horizon. And once you see it, it becomes obvious that it's a moving object. It becomes obvious that it is what it is. So the question is, how could you have gone all these years without seeing it? There's sort of a needle in a haystack kind of syndrome going on here, where the thing has been hiding in plain sight for all of these years. You just haven't really taken the time to look for it. But once you see it, you can see the obviousness of it. And that's true with a lot of things in this world, is that there's a lot of things going on that you currently don't see. But with a little bit of patience and a little bit of technique, once you learn how to see these things that are not so obvious, they will become obvious to you, and you'll wonder why you were never able to see them before. All right? So let's delve a little bit into probability and statistics, and I promise I won't go too deep. If I were to flip a coin, what are the chances that I would end up having that coin come out heads? Okay, and I'm sure that most of you know that it's a 50% chance. It's either going to be heads or tails, and it's 50-50, one or the other. So you've got a 1 in 2 chance of flipping heads. What are the chances that I could flip heads twice in a row? Well, it's 50% chance of getting it the first time, and then if I do it a second time, that's actually a 1 in 4 or a 25% chance. All right, and there's actually an equation here that's basically 2 raised to the nth power, where n is the number of flips. So if you're going to flip it twice, you would have 2 raised to 2, and which is 2 times 2, and that's 4. So the chances are 25%, 1 in 4, that you will get heads twice in a row, or tails twice in a row. And you can take that to any number of flips. So for example, if you're going to, what are the chances you would get heads 10 times in a row? Well, that would be 2 raised to the 10, which I believe, I'll double check this, but it's 1024. So there's one chance in 1,024 flips that will come up heads 10 times in a row. There's lots of ways to express the probability of something occurring. One is by a percentage. If I flip a coin once, I've got a 50% chance of it coming up heads. If I flip it twice, I've got a 25% chance of having it come up heads twice in a row. But what we find is, when the numbers get large and the chances get small, the percentage is like, 0.001 versus 0.0092, whatever. And it's hard to grasp in your mind what those small percentages, whether that's a ridiculously small percentage or just somewhat small percentage. And so what we try to do is try to express it in terms of a probability, in terms of a ratio of events. So, for example, if we want to flip a coin 10 times, what are the chances that it'll come up heads 10 times in a row? It would be, there is a percentage that we could use, but that percentage is meaningless to our brains. We can't really, it's hard for us to grasp what those percentages mean. It's a lot easier to grasp the idea that it'll happen once in 1,024 attempts. So if you sit there and you flip it 1,024 times, you would expect that somewhere in that period of time of doing it 1,024 times, 10 times in a row would have come up heads. That's not saying it definitely will happen. It's saying on average it should happen every 1024. So let's say you flipped it 500 times and it came up 10 times in that period of time. It came up heads 10 times. Is that super unusual, or is that just a little bit strange? And so that's where we get into statistical analysis. So, and we're going to talk about that a little bit in a minute. But the point is, we are going to talk about probabilities in terms of how often something will happen, how many times you have to do something for that event to, reasonably on average, for that event to happen. Another way to take a look at statistics is a graph. And a typical graph is going to look like this. I'm just going to draw it here. If I was doing this live, I would draw it on the whiteboard. That's a typical graph of a probability distribution. Now, you might have a teacher who is grading tests, and she's trying to figure out what should be an A, what should be a B, and what should be a C. And maybe the teacher would have a graph like this and would say, the people who got 90% on the test, there was only, oh, and the number, okay? The number of events is over here. So the number of people who got 90% on their test is way down here. Maybe it's 1. So I'm going to go 1, 2, 3, 4, 5, ... 10. So here we go. There's only maybe 1 or 2 people ended up getting a 90. And if we go to 80, it intersects the curve here, and we go over here, and maybe 4 people. 70, we ended up getting 9 people, etc., etc. So the teacher will take a look at this graph, and will figure out a C is probably in this range. A B is probably in that range. An A is probably in that range. And a D is here. And a failing is probably down here, right? If this graph moved, let's say the average person ended up getting a 60. Let's say it said 60 right here. Well, maybe the teacher would grade on a curve and decide that, you know what, the bulk of the students got a 60, so I'm going to make that a C. And it looks like no one got a 90. It looks like just the top few people got an 80, so I'm going to make that an A. Okay? So that's where graphical analysis comes in handy. This is a very, very powerful way to analyze statistical data. So the two ways we're going to, or two things we're going to be talking about when it comes to probabilities, we're going to talk about the probability of something happen in terms of a ratio of the event versus how many attempts it takes to get that event to happen, or we'll show it as a graph. All right? So those are the two ways, and very often that graph is called a bell curve. All right? So those are the ways of measuring data. Let's talk a little bit about some data that might come up. I'm going to talk for a minute about some data that would come up. I'm just inserting this in the video stream because what I did on the original video, I made some mistakes in my calculations, and so I'd really rather sort of do this again. So let's talk about the first example of some data that might come up, and so we can talk about statistical analysis. Let's take an example where we've got 10 people in a room, and I want to find out the chances of, or I want to find out the statistics involved with people's birthdays and whether they're on odd or even days. And so I've got 10 people in the room, and so I'm going to ask who was born on odd and who was born on even days. And we should expect the distribution to be, if there's 10 people in the room, we should expect the distribution to be something like 5 odd and 5 even, or 6 odd and 4 even. Should be somewhere in the middle of that bell curve that we were talking about a few minutes ago. We would absolutely not expect 10 odd or 10 even, right? So you would kind of expect the results to be somewhere in the middle of the curve. But let's take a case where we do get, 10 people who raised their hands and said they were born on an even day. So everyone in that room, all 10 people were born on an even day. What are the chances of that happening? That's pretty incredible, right? Well, it turns out that it's not really that incredible. It's about 500 to 1 chance that everyone in the room would be born on even or on the same day, whether it's even or odd. About 500 to 1. That's rare, but it's not crazy rare. And so if you were to take that data to someone, to say a traditional scientist, and try to prove some paranormal event, they would look at that data and go, 500 to 1, yeah, that's interesting, but that's not overwhelmingly that's not an overwhelming number. And so that's the problem we get into in a lot of cases with some of these paranormal kinds of statistics, is that you'll see something that's interesting, but it's not overwhelmingly convincing, I should say. And so there's a method that we can use called metadata analysis, which is an important tool. And here's how it works. If we have a room with 10 people in it, and we get all 10 people born on an even or an odd day, that's interesting, but that's not overwhelmingly convincing. What if we were to run that same test in classrooms across the country and around the world? Let's say we ran that in 1,000 different places around the world, 2,000 places around the world. And let's say they all came up with numbers like 10 and 0, 10 even and 0 odd. Well, now you've got a ridiculously convincing set of test data, if you can combine all that data together and treat it as one test. And that's what metadata analysis does. So if you have a test that you run, you can take all other runs of that test that happened perhaps 10 years ago. You can combine all of these tests that show these results and report them as a single test. That's what metadata analysis does. And it really allows you to, in a lot of cases, take data that was marginally convincing and turn it into something that's much more than that. So that's the type of thing that is done in a lot of cases with paranormal work. It bothers some scientists, but it's used in lots of disciplines. It's used, for example, in the pharmaceutical industry to combine tests on medications, etc. So it's generally considered to be a valid approach, although you need to be very, very careful about certain things. For example, you got to make sure that people aren't running tests and throwing the data away if it didn't show results that they wanted to see. I mean, if someone ran a certain test and it showed a result that disproved whatever it is you're trying to prove, you're not allowed to throw that test data away. You cannot selectively go in and pick test data that you're going to use to prove your point. So you need to be really careful if you're going to do metadata analysis to manage all of that data and not pick through it and sort through it and just pick the convincing data. So that is a method that's going to be very important as we go forward, and that's a method you're going to read about if you read various of these scientific analyses of paranormal events. So, again, when it comes to statistics, we're going to talk about the probability of our occurrence happening as a ratio. We're going to talk about using a bell curve to see where this event plots out on a bell curve. Is it way out here on the end where it's got a very small chance of happening, or is it right in the middle, which is where the average event should happen? And we're going to talk about metadata analysis, which is an important part of combining individual tests to get much more convincing results. All right, so let's talk about a couple of cases. And it's very hard for me to do the visuals in this kind of setting, but I'll try to give you the basic idea. So the first test we're going to talk about, it's called a ball drop test. Basically what you've got is, imagine a wall with a bunch of little spikes or little sticks sticking out of the wall, okay? And every few inches there's a stick sticking out of the wall, and then there's a piece of plexiglass over the top of those sticks. At the bottom of this wall there is a box like this with these columns in it, okay? So we're going to have all these columns. And so basically what I'm talking about is we're going to take a ball, and you got a little door at the top here, a little door with a little chute, and I'm going to drop a ball in the top here, and the ball is going to go clink, 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 clink. It's going to hit these sticks on the way down, and the ball is going to fall into one of these chutes. All right? And then you're going to drop another ball, and it's going to go clinky, clinky, clink, and it's going to hit all kinds of sticks, all these little kind of rods on the way down, and it's going to fall into a chute. And let's say, we drop some number, maybe it's 100 balls, one at a time. What would you expect the distribution of these balls, how would you expect them to stack up in these columns? I'm going to draw what I would expect to see, okay, in these columns, and you tell me whether you recognize the shape of what I'm talking about. Okay, here's what you would expect to see if you drop these balls this way. You would expect to see most of the balls end up directly below, even though they bounced all over the place. On average, if they bounced this way, they would hit a rod and they would bounce back. They would bounce this way and back and this way and back, and they would end up falling directly below where the ball was dropped. Some of them would end up to the left and to the right of that position, and then a fewer number would end up further to the left or the right, and so on and so on. Look at the shape of this curve. Doesn't it look just like that curve? Doesn't it look like a bell curve? Well, in fact, it is. That's exactly what it's going to look like. That's the way the world works in a lot of cases. It's very probabilistic. So you're going to design experiments that give you results that are exactly what you would expect, or you'd have data falling around a central point or a mean. And that's exactly what you've got here. You've got balls falling around a central point or a mean, which is where you drop the ball. Okay? Here's where it gets interesting. There's nothing terribly interesting about that, I don't think. It's kind of what you would expect. Here's where things get strange. This test has been run hundreds, maybe thousands of times in front of thousands of audiences. And what the person running the test asked basically before they dropped any balls, when this was all empty, they would ask the crowd to, and I'm going to put an R here and an L here. Okay? I'm going to put right and left. And what they would ask the crowd is to, the procedure varies, but sometimes they would flip a coin, and there would be an R on one side of the coin and an L on another, or it'd be heads and tails, and they would say R for heads and L for tails, whatever. They would flip a coin, and they would randomly pick L or R. And then they would tell the audience to concentrate and try to make, let's say we flipped the coin and we came up with R. They would ask the audience to use their intention, to use their concentration, to try to get the balls to go to the right side of this little catch area. And they would allow everybody to get into a nice, peaceful, meditative state of mind and to concentrate on getting the balls to fall to the right. And once everyone was in the right state of mind, they would start dropping the balls. And yeah, you guessed it. What you find is, consistently, not universally, but what you find is the balls are being skewed in the direction of the intention more than statistics would have predicted. And let me explain what I mean by that. You would expect that if you run the test and then you say concentrate on going to the right, and then you run the test again, you would expect one test after another, the results are going to vary, a little bit left, a little bit right. So, is it possible that you're going to do a test and then say concentrate on going right and do a test, and then the balls would be a little bit skewed to the right? Absolutely, that's expected. There's nothing that's proven by that. However, two things. First of all, if you run the test over and over again multiple times, you would not expect it to be, and let's say you ran the test 10 times, you would not expect it 8 times to have it skew to the right and twice skew to the left. You would not expect that. That is statistically anomalous. Also, you would not expect all of a sudden, you would not expect that bell curve to shift dramatically. If it shifts dramatically, that is statistically significant. And if it shifts from run to run to run, if it shifts more often to one side than another in a significant way. In other words, if you've got 10 runs, if it's 4 this way and 6 that way, that doesn't mean too much. If it's 8 this way and 2 that way, it does mean something. Well, what does it mean? Well, that's when you get into data analysis, and there are mathematical formulas. You can plug in this data, and it'll come back with a probability of that occurring. And I'm going to pick a probability because I don't have one in front of me to use, but on a particular test, doing this sort of experiment, you might find that the results are 1 in 10,000 that result might have happened, 1 in 20,000, 1 in 5,000. Okay, so that's pretty significant. It has been found that through intention, people are able to cause these balls to shift in a significant way, statistically, based on their intention. That's pretty incredible. To me, that's, if you're creating a list of proofs as to prove whether or not this paranormal stuff is believable, you ought to put that as item number 1 on your list, that something like this could happen. All right? So that's the ball drop test. Let me give you another test that's pretty incredible as well. This is, I guess I'm just going to call it the medical records experiment. This is a retrospective experiment, meaning we're going to take data that already exists. We're going to take events that have already happened, and we're going to run an experiment to see if we can affect that data. Okay? See if we can essentially affect stuff that's already occurred. It'd be pretty incredible if we could. Anyway, so let's talk about how we do this. Medical researchers went and gathered some medical records from a cancer treatment center. And these are medical records that are multiple years old, that are patients who were undergoing cancer treatment, and that treatment was either successful, the cancer was cured, or cured to enough of a degree where you could call it a success, or was unsuccessful and the patient usually died. Those are the two sort of binary operations. Success, I lived. Failure, they died. So there's thousands of these things, and what they did is they took a couple of groups, and so I'm going to create some numbers for you so we have something to talk about. I'm going to reach in, I'm going to randomly grab 100 of these files, and I'm going to put them in this pile. And I'm going to randomly grab another 100, and I'm going to stick them in that pile. So now I've got 200, I've got 100 random records over here and 100 random records over here. And I split each one of those 2 piles into 2 piles. So I've got 50 and 50 on my right side and 50 and 50 on my left side. What I do is, I am going to take one of those 2, the ones on my left, I'm going to take them and I'm going to just put them aside. I'm going to take the ones on my right, and I'm going to mark one of the folders with an A and one of the folders with a B. So I've got an A folder and a B folder over here on my right-hand side. And I've got this group of meditators, and I'm going to ask them to pray or to show positive intention, positive outcome for one of these folders. And we're going to flip a coin, and we're going to pick a folder, and we're going to do that. So let's just say we flip a coin and we pick folder B. I'm going to ask them to show positive intention for all of the records in folder B for a positive outcome. And I'm going to ask them to ignore folder A. Okay? And I'm going to have them do that for a particular period of time, let's say 20 minutes. Then what I'm going to do is, now I'm going to take a look at the actual data. So what I'm going to do is, I'm going to go over to my left-hand pile. Remember, my left-hand side, I've got two folders over there of 50 records each. And I have no idea what's in those records. I have no idea what the results are. But now I'm going to open those folders. And what I'm going to do is, I'm going to go through the first folder, and I'm going to tally up the number of positive versus negative results in that folder. And I would expect it, well, I don't know what the number is, but let's say, just for argument's sake, let's say it was 75% positive and 25% negative in that first folder. Then I'm going to open that second folder and I'm going to go through that. I would assume that if the first folder was 7525, that the second folder should be something like 7525 as well. Because remember, these are all random cases taken out of a random file. Whatever the random success rate ought to be somewhat consistent throughout all of these folders. So I take a look at the second folder, and lo and behold, I get about a 75-25 ratio. So I've really got a case where I've got these two folders over here that kind of agree with each other. They have approximately the same success rate, which is exactly what I would expect because they're just random files that I didn't do anything with. Now I'm going to grab the two folders on my right. First, let's take a look at the folder that we didn't do anything with. The folder, I think it was A, that we didn't do anything with, and I look at it. What I would again expect is that that number should be something like 75-25. It should be similar to what I found on the other folders. And in fact, that's what researchers typically find. It's not going to be the exact same because statistically it's going to vary. But if we were to show the results on a bell curve like this, we would find that all three of those folders, the two left folders and the A folder on the right, are all going to be somewhat located in the middle of this curve. No surprises yet. Here's where the surprise is, and you probably know exactly what I'm going to say, because you know this. Well, you're probably going to guess. Anyways, so I'm going to grab folder B and look at it, and what do you think happens? Well, we had the people in the audience showing the intention of increasing the survival rate of these cancers. And what we find is 80%, 20% in that folder instead of 75-25. Again, I'm making up numbers just as an illustration. The point is, the three folders that we did nothing with all agree. The one folder that we showed positive intention on, we changed the outcome of that data in a statistically significant way. And the chances against that one folder being positive versus having a positive data relative to the other three folders, the chances against that are thousands and thousands to one. Okay? So that is the medical records experiment. This has been done multiple times, and I like to think of it as the power of intention. You'll actually find if you do any research, very often it's referred to the power of prayer, which is essentially the same thing. Keep in mind what we're doing. These people either lived or died. They were either cured or not cured years ago, right? We're not talking about talking to a patient and making them feel good and encouraging them that they're going to be okay and then they have a good outcome. We're talking about patients that may have died of old age by now. We've actually gone in retrospectively and changed the survival rate of that cancer with nothing except the positive intention of a bunch of meditators. Well, there you go. So to me, again, this has been done enough times and in controlled enough ways that I believe that this is indicative of something very odd going on in our world. So I put that as item number 2 on my list of why to really, pay attention to these paranormal kinds of events. Now, any one particular test, science either already has or could create an argument to say why that's an invalid test. I understand that. That's why we're going to be talking about dozens and dozens of different kinds of indications that what we're talking about is true. Because all of these things can't be faked. It's just ridiculous to think that every single one of these items is faked in some particular way to prove something that is untrue. That's just, I'm not a conspiracy theorist. I don't believe that, there are that many people in the world that are trying that hard to fake this kind of thing. That's what the researchers have found. I'm going to give you one more example that is actually, I believe, more incredible than the first two. This is, I'm going to talk about a random number generator project that's been going on for some time. There is a project, it's referred to as the Global Consciousness Project. You can go on, you can Google it. And what it is, it's a bunch of computers around the world, and each one of these computers is generating random numbers all day long. That's all they do is generate random numbers. And the interesting thing about random numbers is you can actually test to see how random the random numbers are. So for example, if I was coming up with random numbers off the top of my head between, say, between 0 and 11, so 1 through 10, I might say 1, 7, 2, 6, 8, 2, 5, 9, 2, 8, 9. Question is, how random was that? Well, I heard myself say 2, I think, twice, maybe 3 times. And so my guess is that wasn't super random, right? And you can actually run those numbers. You can run that string of numbers through a mathematical formula that will come back and tell you how random the random number was. And you can plot that on a graph. So, for example, you might have a graph that looks like this. Okay, this is sort of a standard graph. And let's say on this particular graph, a completely random number, I'm going to put a dotted line there, a completely random number would run right along that dotted line. And so if you were to plot a random number generator, if that would generate a line that went straight across here, this is the first random number it creates, and the second, and the third, and the fourth, and the fifth, and the sixth. So this is shows you the numbers that are being generated, and this shows you how random they are. You would love to see a line that went straight across like that. What I probably just read off to you was something that was like maybe a little bit random, but then not very random, right? Something like that, right? That's not very random. A straight line here would be random. So anyways, let's get back to the project. They created all these, they set up all these computers around the world that generate random numbers all day long. And they all provide their random numbers to a central computer. And that central computer looks at all the random numbers generated from all the different computers in the world. And it does a plot to show you how random the numbers are. And if you go onto that website, you will actually see a plot. And on a typical day, you're going to see it going like this, and it's going to go up and down. You're going to see it vary, but it's going to vary back and forth around a perfect random number, right? It's going to vary, but it's going to go up and down based on the perfect random number. But if you ever see it go like this, and then back down to random, that's very, very odd. And again, part of the random number project, part of this global consciousness project is they can tell you statistically the chances of that anomaly happening, that anomaly I just showed you, where the random number generators all of a sudden became non-random. And it does happen. They do become non-random sometimes. And the question is, why should that be the case? Not only why should a particular random number generator become less than random, why would that happen across 10 or 20 or 30 or 100 computers? Why would, in aggregate, why would they all become non-random, right? Maybe you have one computer becoming non-random just because statistically, that's going to happen occasionally. But it wouldn't be coordinated with other computers going non-random at the same time, all right? So far we've been talking about theoreticals. Now let's talk about what they actually found. And what they actually found was rather incredible. What they're finding is that, first of all, as we've discussed with the last couple of tests that we've run, the medical records experiment and the ball drop experiment, there seems to be some way that the intention or the thoughts of people can somehow affect real-world stuff. Somehow, wanting the ball to fall on the right side of the board instead of the left actually causes the ball to fall on the right side of the board in some significant way. No, you can't make all the balls fall on the right, but it seems like you can give probability a little bit of a shove to the right. Well, researchers took a look at this random number generator, and they saw that occasionally, worldwide, the random number generators would start deviating from random. And what they found out was that it seemed to coincide with events that focused a large percentage of the population of the world. Incredible but true. And so one of the data points that they used was Princess Di's funeral. That was, I believe, one of the most widely televised events in world history, was Princess Di's funeral. It was worldwide. It was on TV. Everybody watched it. Everybody was focused on the same event, and most people were sharing a similar emotional state at the time. Essentially what was happening is the world was being somehow all sort of coming into synchronization. The world was all kind of had a shared focus and a shared emotion. And what happened was the random numbers weren't random anymore, and they became ultra unrandom. And the chances against all these machines going non-random for that period of time, that much, is, I believe, the numbers are billions to one. And then when the funeral was over, everything came back to normal. All the random numbers went back to normal. Think of the most dramatic events that have happened in the last, well, this system has been running for, I don't know, since the 1990s. Think of the most significant events that have happened since the 1990s. And anyone, give me some examples of significant, maybe traumatic events that have happened in the world that might have focused the world's attention. And I'll give you a chance to respond, but I'm all by myself in this room. So I'm going to come up with I'm going to come up with three. One of them is older than the 1990s, but say the JFK assassination. Everybody remembers that was alive at that time, where they were, what they were doing, and how they felt when JFK was assassinated. But that was before this random number project existed, so we'll just have to throw that out. I'm just sort of throwing that out there as an example. In the current generation, the current time frame, how about the Challenger disaster? How about the shuttle where all the school kids in the country were sitting there watching TV and saw the Challenger explode? How about that as a unifying event that everybody shared? Guess what? If you take a look at the random numbers around that time, around those few hours when the Challenger disaster happened, all these machines went non-random. And then again, it settled back down. Wow. You know, a lot of these things you need to see multiple occurrences of the same thing happening so that you can really believe it. Okay, now the ultimate worldwide focused event that happened in the last 20 years, it focused the entire world, would be what? Can anyone say 9/11? It would be 9/11. And yes, in fact, these computers went completely non-random when 9/11 happened. So it really is a demonstration that this thing is real. How does it work? How does this actually happen? We're going to have to understand a lot more about metaphysics to figure that out. But it seems as though there's something here, something worth looking at. There's one last piece of information that I find stunning. Okay? And that is, not only does this, in the case of specifically in 9/11, and this may be true with some of these other cases as well, I think it actually is true. The machines went non-random about an hour before the event happened. Somehow, world consciousness was affecting the random number generators a little bit before 9/11 occurred. Guess that means in some odd way, we all sort of knew that this was going to happen just before it happened. And this has actually been found in multiple types of paranormal tests. It's even been found in muscle tests where, and brain scan tests where a patient is asked a question or asked to respond to something, or actually is, well, I'll give you the example. There's an example where, a test where images are flashed on a screen in front of a subject. and the subject is instrumented with brain wave sensors. And their images are flashed on the screen, and the images are either sedate and calm, or they're very disturbing. And the sedate and calm ones are a picture of a calm beach, a picture of a flower, a picture of a kitten. And the disturbing ones are just bloody, nasty, ugly pictures. And they're put up on the screen at random intervals. And I think the intervals are between 1 second and 5 seconds. So randomly, these pictures are put up on the screen. And randomly, they're positive pictures, and randomly, they're negative pictures. And as you might imagine, when a person is looking at a calm scene of a kitten, your brain patterns look a certain way. When people are looking at some awful scene from a war, their brain is much different in terms of the waveforms. So it's very, very easy for a researcher to sit there and look at the brain waves and know whether the patient is looking at a calm scene or some sort of a horrendous scene. What they find is when the calm picture comes up, everything is calm on the brain scan, and when the nasty picture comes up, everything is erratic on the brain scan. But here's where things get interesting, is that a split second before the picture comes up, what the researchers found is that the brain would actually go into its calm or erratic state before the picture would even be displayed to the person. How's that possible? I mean, the computer hadn't even decided which picture to display yet, but somehow the human being involved in this test, somehow they knew that the next picture was going to be either calm or horrendous. Again, they were precognitive in their ability to be able to know which picture was going to be displayed. In the same way that we precognitively knew that 9/11 was going to happen an hour before it happened, and somehow we had an effect on random number generators across the world because of that. Pretty incredible stuff. So I would put that on my list as well in terms of, reasons to give this some thought. Bottom line of this whole unit is our thoughts, our intention affect the physical world. It's been proven. It is indisputable. Somehow, we humans, and maybe even other life forms as well, but mostly I'm talking about we humans right now. We humans, just by the power of our intention, the power of what we expect or want to happen, we can affect what actually does happen. That's not supposed to be the case in a materialistic, mechanized world that doesn't believe in this woo-woo stuff. All right? So that's it for unit number 2. Unit number 3 talks about how our senses work, and we'll get to that next.